So these green lines all go to the NOR gate, and the output of the NOR gate, one of them goes to the chip enable of the RAM, and the other one goes to the chip enable of the ROM. So basically what it does is it takes in the high addresses, and if any of the high addresses are active, then the RAM will be enabled, and if the high addresses are not enabled, then the ROM is enabled. Because again, the ROM is only 8 kilobytes versus the RAM, which is up to 512 kilobytes. The high addresses, like really high address pins, like address, I believe 17, 16, are tied to ground, and then the rest of it can be read by RAM. So basically any address that's addressed in something that's higher than 8 kilobytes in space will go to RAM instead of the ROM. And then if we go over here, I have this little program right here that actually uses calls and stack pushes and pops. So the idea is that you have call this output 1 function. So we should load the value 1, and we should output it onto the 7-segment display. Then we return. So we go to this line here where it's load byte 2, we output 2. Then we should call the function output 2. Go to output 2. We'll load the value 3, output that, return. Then here we have a plain old load byte 4. We should output that. Then we should load the value 7, push that into the stack, load the value 6, push that into the stack, then load the value 5, push that into the stack. Then we pop all these outputs off the stack, so we go in reverse order, so we should see the value 5, 6, and 7 outputted. So again, it should do 1, 2, 3, 4, 5, 6, 7. And what's cool is that we're using the stack pointer. So all the way over here, this stack pointer for the calls, it's going to save the program counter, which is over here. It's all this circuitry over here. This is the program counter. So it saves the lowest 8 bits of the program counter onto the stack, increments it, then saves the highest 8 bits of the program counter, saves that onto the stack, which is, the stack is all this, it's inside RAM, and it's just a hardware-based pointer over here. And then when we return, we just pop the stack. We pop the last 2 values of the stack and put that in the program counter high, then put it in the program counter low. So, and the same idea goes for the push and the pops. It's even simpler. You just take whatever values in the T register, which is right here, take the T register, push that onto the stack, which is incrementing the stack and saving it, and then pop NIT, which is incrementing the stack and retrieving that value at that address. So let me just step through this program really quick. We're running at around 2 hertz, and then right here when I flip this to the right, the reset line is disabled. So it's going to run a little slow. We can see here it's stepping through the states. I can speed it up a little bit. So now I'm going to run it at like around 5 hertz. So we're at 1, 2, and it should be 3, 4, 5. Anyway, some of these instructions, they take a little more states. This is the state register incrementing right over here. We're going through a set of finite amount of states to implement an instruction. This is the instruction register, and this is the condition line. And we're going to miss it, and it goes 6, 7. The pops take really quick. It's what really takes the time is actually the calls take a fair amount of time because the RAM is level triggered, not edge triggered. So you have to make sure that the T register, when it's written into RAM, is like a stable value on the data bus. And the data bus is right here, goes across here, and goes all the way here into the output register, which is decoded by these east-west prompts, which have the corresponding values on the 7-segment display just programmed on there.